My name is Mahtab Heydari, and today I'll be discussing common problems found in prestressed concrete. So, for some background, as we've learned, prestressed concrete works by imposing a longitudinal prestressed force on a concrete member, and as you can see in this animation here, high-strength steel strands are first inserted into the concrete form prior to the pouring and curing of concrete. And these strands are tensioned, and once the strands are cut, the prestressing force is transferred from the steel strand to the concrete, exerting a compressive stress on the concrete itself prior to the application of any external loading. The first problem we'll discuss is cracking due to corrosion. Now, cracking due to corrosion is one of the main causes of deterioration in prestressed concrete structures, leading to a number of problems which can eventually deteriorate the structural capacity of the member. Corrosion products can build up around the strand concrete interface and create an expansive stress concentration. Cracks from corrosion alone don't necessarily pose any threat to the structural performance of the member, but left untreated, harmful substances such as de-icing salts or other contaminants can leak into the structure via channels created. So here's a schematic of 7-wire strand and how corrosion can lead to crack and the crack propagation. So first, in this figure on the left, you can see corrosion products building up around the strand concrete interface. And since concrete is a composite material, this interface is a porous zone in which corrosion products can enter. In this figure in the middle, we have a micro crack that is formed, and this occurs once the tangential stress reaches the tensile strength of the concrete. And after the micro crack formation, corrosion products can continue to build up around the strand, leading to expansive pressure-induced cover cracking. And with further corrosion, this crack can propagate all the way up until the surface, producing a visible crack. And this is normally when any repair and maintenance would be performed. So, a 1982 study looked at all cases related to prestressed steel corrosion in the United States. Of these 50 total cases, 10 of them involved brittle failure in one or more steel tendons. And looking in at one of these cases, we have an elevated building slab over a parking area. This was a lightweight concrete slab supported by columns, which were then supported by concrete pile foundations. And the strands were unbonded, greased, and paper wrapped, which we'll discuss why that was important later. Brittle failure began 40 days post-tensioning and continued sporadically, mostly in the areas of highest negative moment over the concrete columns. So, it turns out that the paper-wrapped strands had a corrugated exterior that was likely cut through during tensioning. The pre-stressing or tensioning process involves a lot of movement at the strands, and it was likely that it was cut through during this process, which exposed the steel strand directly to the surrounding aggregate, likely causing the corrosion. And in this case, the brittle failure, or the strands that had failed, were analyzed using etching, and the results of that are shown in the background here, as you can see. And it turns out that hydrogen sulfide embrittlement most likely caused the delayed onset of the failure in some of the tendons. One thing that was learned from this was that using plastic or polymer sheathing to debalance strands is much more effective than paper wrapping. This is the way it is done most of the time in the United States today. And the smooth interior and exterior ensures that the strand can withstand the movement associated with pre-stressing and won't be cut through. The next problem we'll look at is cracking in the pre-tensioned anchorage zone. The anchorage zone is most commonly associated with the end zone of a bridge girder, closest to where any hydraulic jacking of the strands occur. And this area is an area of very high concentration of pre-stressing force. The transfer of heavy pre-stressing force to the concrete is what leads to the cracking, and these cracks are proportional to the amount of pre-stressed force on the girder, which is also proportional to the size of the girder. This cracking can first appear during pre-stressing, but These girders are often stored for months at a time before any application on site during construction, and the cracking can continue to grow during this time period. Similar to cracking due to corrosion, these cracks on their own don't necessarily pose a threat, but left untreated, they can allow contaminants like de-icing salts or others to reach the steel strands and further deteriorate the structure faster than expected. Here is the anchorage zone illustrated on the left and right. The cracking tends to follow a similar pattern as shown by multiple case studies, and several studies have looked at the factors that play into anchorage zone cracking. Some looked at temperature effects or thermal stresses caused by curing, or creep and shrinkage that occurs during storage. And an FEM-based investigation showed that shrinkage actually had the most unfavorable effect on anchorage zone cracks compared to creep and thermal stresses. Repair of these cracks can be costly and time-consuming, and most commonly an epoxy injection along the length of the crack is what's used, which can detract from the physical appearance of the concrete member, but also can delay production. A number of crack control methods can be used to prevent and control the cracks during the design stage and during the pre-stressing stage. So one method that can be used on the design end is designing for a diagonal compressive strut, carrying the shear force to intercept these cracks, or additional live loading to help seal the cracks. Another method, as I discussed before, is using polymer sheaths to debond a number of strands towards the end of the girder. Note that only 40% of any row or 20% of total strands should be debonded per most DOT's guidelines. Another method is strand cutting pattern. I know a number of studies look at the order in which you cut strands in the pattern and how that can help control anchorage zone cracking. And lastly, placing larger reinforcement at the very end of the girder could counteract the effects due to shrinkage. So, in conclusion, cracks on their own in pre-stressed members don't pose an immediate threat to structural performance, but maintenance can be time-consuming and costly, and can eventually lead to further problems left untreated. A number of design considerations can be made on the front end to better predict and control cracking in pre-stressed members, and multiple case studies reveal that using polymer sheathing to debond or protect steel strands can improve long-term durability in pre-stressed members. These are my references, and thank you for watching.